Okay, we're going to work on our first CAPM problem here using graphical solving. So we have a motorcycle racing a jet. We're going to approximate that the motorcycle is pretty much at CAPM because it accelerates up to that speed much more quickly than the jet does, while the jet increases its speed at a rate of 4.5 meters per second from rest. So we want to know how far down the road and at what time the jet will catch the motorcycle. Okay, so here's our v versus t graph. Nobody's ever going in the other direction, so I'm not going to have anything be negative. Alright, so we're going to do a v graph in meters per second. Make 10 meters per second the tick length, so 10, 20, 30, 45. That'll be our motorcycle. And the jet starts from rest, and it's going to increase its speed as we go at a constant rate. So we should have a linear v versus t graph. Now, I'm not actually going to label any values on the time axis. Okay, what we're going to do is use the shape of the v-graph to determine some equations that we can solve for it, so that we're going to actually end up with a little bit more accurate result than we did with our CVPM graphical solving. So what we're looking for is for the two displacements to be equal. That's the first thing I need to realize, that the delta x of the motorcycle needs to equal the delta x of the jet. That's the condition we're looking for. And on the v-graph, delta x is the area underneath the v-graph. So if I look at, say, this point, this seems to be the first interesting point, what's happening here? Well, since this is a velocity graph, what it means is that they're going the same speed. But if you look at the two areas, that one's for the jet, and this one's for the motorcycle. You see the motorcycle is actually far ahead at this point. So that is not the point we want. So it's going to be somewhere down the road when the jet is going faster than the motorcycle and has had a chance to catch up. We can actually solve this problem by symmetry, but I want to make sure that we have tools to solve it when the situation is not quite so neat. So let's say that it's this point, sometime down the road, where the jet catches the motorcycle. So that is sometime delta t. And both the motorcycle and the jet have been traveling for a time delta t. So the delta x for the motorcycle is this area. And the height of this rectangle is the velocity of the motorcycle. So that area here, we know is velocity of motorcycle times delta t. That's the height, and that's the length of the area. And we'll change colors for the jet here. So the jet's area is this one. So that's a triangle. So we're going to need to write an expression for the area of a triangle. We know it's 1/2 the base times the height, and the base is still delta t. So 1/2 delta t, that's cool. The height of the triangle, though, is the vf for the jet, the final velocity of the jet, which we need to figure out how to get because we don't know what that is right off the top. But what we do know is the rate at which the velocity changes. We know the acceleration. We know that we start at a 0 velocity. So how far have we increased our velocity during this amount of time? Well, if the acceleration is the slope of that graph, the final velocity of the jet is the acceleration times the amount of time it's been accelerating for since it started from rest. So that's not something that will always be true, but that's true in this case. So I can rewrite this right side like that. And now I can solve. If I simplify this right side a little bit, cancel the delta t, and solve for delta t. We'll check our units. So the meters per second cancels out. We have a seconds in the denominator left over. That goes up to the numerator because of the compound fraction. And so we get 90 in the top divided by 4.5, which is 20 seconds. You can see by the symmetry of the problem you might have gotten that. It's at 10 seconds when the two have equal speeds, and then you have to go 10 more seconds so that the area of this top little triangle equals the area of that triangle that was left out. But we're trying to develop a more general approach that will help us everywhere when it's not so symmetrical. And if we want to know where that is, we can look at either the v delta t for the motorcycle, now that we know the delta t, or we can look at the expression that we came up with for the jet. And they'll both tell us 900 meters. So that's where it catches, at 900 meters down the runway with 20 seconds having passed.